Hello everyone and welcome to lecture. Today's lecture will be about multivariable functions and critical points. So multivariable functions and the critical points of multivariable functions. And this is going to be related to the idea of single variable multivariable functions. So the idea here is that we're going to start off by reviewing the definition of a critical point for a single variable function and see how this almost directly generalizes to multivariable functions. So recall from 1D calculus, right, in 1D, for a given function of x, say we have y is some function of x, we can have two main types of critical points. For instance, this function might come up to some maximum here and hit a local minimum right here. Maybe there's an inflection point of the function. So it kind of comes up, goes down, and there's a point where the concavity changes, and then maybe you have some discontinuity, so a cusp point right here in the derivative. This is a nice picture, say, of a possible example function of x. And we'll just kind of consider the interval, say, from a, so from right here, to b, right here. So on this interval from a to b, this function has, looks like it has 4 critical points. x1, x2, x3, and then x4 right here. And these are all critical points of the function because they're all points where either one of two things is true. At each one of these points on this interval, so say a point x star is a critical point of a function f of x in 1D if either the derivative at x star, the rate of change of the function f at x star, is equal to 0, or the derivative at x star does not exist. which we'll abbreviate as DNE for short. So here you can see that x1, x2, and x3 are all critical points of type 1. Because the slope at x1, the slope of the tangent line at x2, and the slope of the tangent line at x3, each one of these has 0 for the rate of change. So each one of these, x1, x2, and x3, are critical points of type 1. Whereas x4 is a critical point of type 2. Or a critical point, it's a critical point x4 because the derivative just does not exist there. The slope does not exist at that point because it's a cusp point, similar to the absolute value function at the origin. And you see that each one of these types of critical points are important to deal with. Both of these types of critical points are important to deal with because in general, both of these types of critical points are points where the function could possibly attain a local max or min. And when it comes to, say, optimization, so optimizing an output of a function or optimizing something, you have to be very, very careful about finding all of the critical points of any given function. So we want to see how to take this idea and directly generalize it to multivariable functions. The main question that we want to ask ourselves is how to take this or generalize this classification to multivariable functions. And the idea is that we have almost a direct generalization for multivariable functions. So what we'll do is I'll write the general classification, and then also we're going to focus on the 2D case. But turns out that this is directly possible to generalize to multivariable functions. For a multivariable function, function f of r, depending on any number of variables, we say that a critical point which we'll denote as r star. It's a vector now because the domain of the multivariable function is in multidimensional space. The critical point r star, I guess we say r star is a critical point if one of the following is true. And the first case is very similar to the first case in the 1D case. It's that the derivative of the function, or in some sense, the derivative of a function is the linear approximation of the function, or the linear approximation of the function, or linearization. This is directly dependent on the gradient vector. So we say that a critical point is a critical point if the gradient vector of the function at the point r star is it's exactly equal to the zero vector. Or the gradient of the function just flat out does not exist. So this is our direct generalization of the idea of a critical point from 1D into ND. Now for 2 dimensions, or for a function of 2 variables, this becomes straightforward in terms of the partial derivatives. What this means is that a critical point for a 2 variable function, or in 2D, if the gradient is equal to the zero vector, then both partial derivatives have to be equal to 0. So the x partial derivative at r star has to be 0, and the y partial derivative of f at r star has to be equal to 0. And likewise, the other type of critical point in 2D for a function is if the gradient vector does not exist, which means that either the x partial derivative at r star does not exist, or the y partial derivative at r star does not exist. Instead of that and symbol, I'll write and. So the idea is that these 2 conditions for our definition of a critical point can be applied to functions of 3 variables or 4 variables as well. But it turns out, when we get to classification of critical points, as a local max or a local min, the idea of doing it in 2D is going to be easiest. We can extend it. It's possible to extend to functions of more than 2 variables, but we're going to stick with functions of 2 variables for this course and for this lecture. So the idea is that the method of computing critical points for a function, just like in the single variable case, ends up being a matter of solving a system, or solving equations that guarantee that this is true at a given point. So like either guarantee that the gradient is equal to 0, or if the partial derivative does not exist, then you'll have to show that one of the limits does not exist for one of the partial derivatives. A good example is the roof function. At certain points on the roof, or the cusp, or if you have like a cusp, say, anytime you have a cusp on your surface. So for instance, let's say you have a surface, or a function of 2 variables with a surface that sort of comes to some cusp, or some point at it right here. This would be a point. This is an example of a critical point of this function, because the partial derivatives don't exist at that cusp. Whereas the critical points of type 1, you expect to have local maxes, local mins, and what are called saddle points of a function, similar to the maximums, local minimums, and the inflection points that you get in 1D for a 1D function. Well, let's go through and see this for an example. And for this example, we'll stick with the function from example 1 of the previous lecture, which is the function f of x, y is equal to x times y times e to the negative x squared plus y squared. Calculated that the partial derivatives of this function were df dx, which was y times 1 minus 2x squared times e to the negative x squared plus y squared, and partial f partial y, which was x times 1 minus 2y squared e to the negative x squared plus y squared. So in order to solve for the critical points, we have to ask ourselves either how many critical points of type 1 are there, how many critical points of type 2 are there. Turns out for this function there are no critical points of type 2. And that's because the exponential function is an infinitely continuous function. It's a nice, smooth function. And the function x squared plus y squared is also continuous. So therefore, e to the negative x squared plus y squared is a very nice, smooth, continuous function. And same thing with the function x times y. So because of that, this multiplication, it's like a multiplication and a composition, is also a very nice, smooth function with infinitely many derivatives. So there are no critical points of type 2, but there definitely are probably going to be critical points of type 1. So we need to figure out how to solve for the critical points of type 1. And in general, this can be done by taking the partial derivatives, setting them equal to 0, and then solving the resulting system of equations that you get. So in this case, we have to set the x partial derivative, which is y times 1 minus 2x squared times e to the negative x squared plus y squared. This has to be equal to 0 at a critical point of type 1. And we also have to set the y partial derivative equal to 0, which amounts to x times 1 minus 2y squared times e to the negative x squared plus y squared equal to 0. So we have a system of two equations that we have to solve, and the solution of this system of two equations for two unknowns x and y, all of the different solutions of this system of equations will give us all of the different critical points for this function, the function we're interested in. Now, it's important to note here that this system is a nonlinear system. Just like for solving for critical points in 1D for one variable functions, you typically get a nonlinear equation that you have to solve for x, which means there are possibly many solutions for the critical point that you're solving for. You could potentially have infinitely many solutions for critical points. If you have like a sine or a cosine in there, you very often will have infinitely many possible values that you can solve for that satisfy the equations that are written down. So for this example right here, we got to figure out the easiest way of simplifying this system and trying to solve it. And the main way we're going to do that is that you want to remember that for any value of u, e to the u will always be strictly positive, will always be greater than 0. And therefore, because e to the u is never equal to 0, you can always divide by e to the u for any exponent u. And that's the first way we're going to rewrite this. If I divide equation 1 by this e to the negative equation 1, and we're also going to do this to equation 2 by e to the negative x squared plus y squared, this will give us the following. Give us two new equations. Call it equation 1 star and equation 2 star. Equation 1 star is going to be y times 1 minus 2x squared is equal to 0, and x times 1 minus 2 y squared is equal to 0. And this system of equations is definitely simpler than the one we started with. And the reason that we can do this in simplification is that that e to the negative x squared plus y squared is always, no matter what x and y are, it'll always be positive. So it won't be 0, and therefore we can divide by it because it's non-zero. Now, if instead it were possible that it equaled 0, you would have to think of some other way of simplifying the system of equations. There'd be some other thing that you'd have to do to kind of simplify that system. But because of the fact that this is we can do this, we get a nice, much simpler system to solve. So the idea then is that we have this new system that we have to solve, and we have to look at and see, well, how can we satisfy this system? What values in x and y, with x and y, are going to give us solutions to this system? And the key thing to do almost always is to start with one of the equations and figure out what values of x and or y will satisfy one of the equations. So in this case, we'll probably start with equation 1 star, and then you can go through and see what that implies about the other equation, equation 2. So let's go through and do this right now. So for equation 1 star, right, this is satisfied if one of two things is true. If y is equal to 0, or if 1 minus 2x squared is equal to 0. If y is equal to 0, then equation 2 star becomes the equation x times 1 minus 0 is equal to 0, or the equation x is equal to 0, which means that our first critical point is the point 0, 0. X equals 0, y equals 0. If 1 minus 2x squared is equal to 0, that means that 1 is equal to 2x squared, or x squared is equal to 1/2, or x is equal to plus or minus the square root of 1 over 2. Which actually give us two other critical points. corresponding to x equals plus or minus 1 over the square root of 2. But this also gives us something else to think about, right? If x equals plus or minus 1 over the square root of 2, we have this is satisfied, so equation 1 star is satisfied, but x is not equal to 0. You have to also guarantee that equation 2 star is satisfied. In equation 2 star, if x is plus or minus the square root of 1 over 2, becomes the equation that plus or minus 1 over the square root of 2 times 1 minus 2y squared is equal to 0. And if we make some more room here so we can see this process out. In its entirety, so the only way of satisfying equation 2 when x is plus or minus 1 over the square root of 2 is having 1 minus 2y squared be equal to 0, which means that y squared is equal to 1/2, or y is also equal to plus or minus 1 over the square root of 2, or the square root of 1 over 2, or 1 over the square root of 2. So we have one critical point from this procedure, and this procedure has given us 4 critical points, a total of 4 critical points. Now I'll to simplify what I'm about to write down, I'll make L, we'll let L be equal to the value 1 over the square root of 2. But from this procedure we have that the critical points are located at L comma L, negative L comma L, negative L comma negative L, and L comma negative L, because what we've just shown is that any combination, right, of plus or minus L for x or for y gives us the value of a critical point. So x could be plus or minus L and y could be plus or minus L. Any combination of those two values will guarantee that this is 0 and this is 0, which satisfies our two equations. Therefore, these are the 4 critical points of our function. So we can visualize this, okay, what this is going to look like. Directly. We plot out our x-axis and our y-axis. We solve for the point x equals 0, y equals 0 is a critical point. The point 1 over the square root of 2, comma 1 over the square root of 2 is a critical point. The point negative 1 over the square root of 2, 1 over the square root of 2 is a critical point. The point negative 1 over the square root of 2, positive, or negative 1 over the square root of 2 is a critical point. And then lastly, the point negative or positive 1 over the square root of 2, negative 1 over the square root of 2 is a critical point. So this function, and the solution to that system of equation gives us 5 total critical points of this function. And if we do a visualization of this function, we can clearly see exactly what this looks like. So using my Python code, I plotted each one of these out, and you can see that what we've computed is exactly correct. So we'll look first at the three-dimensional plot, which is the bottom plot here. And you can see very clearly that if we kind of rotate this function around, we're seeing exactly those 5 critical points that we calculated before. And from the plot, you can see that 2 of these points are local maximums of our function. 2 of these points are local minimums of our function. And 1 of these points is exactly a saddle point. So the origin is what's called a saddle point of our function. And a little bit later on in the course, we'll talk about exactly how to classify the critical points for a function of 2 variables. We can get classification tests for functions of more than 2 variables, but the more variables you have, the more complicated, in some sense, these classification tests become. But it's still possible to derive general classification tests. But it's probably shown a little bit more clearly in the other plots. So you can see the three-dimensional plot clearly is showing that we have a saddle point, and then 2 local maxes and 2 local mins. But if we consider either the density plot or the contour plot, right, we're also seeing exactly this. And it probably shows it a little bit more clear that the point plus L and minus L plus minus L are local maximums of our function, because the gradient vector is pointing in around each one of these points. The local minimums, negative L positive L, or positive L negative L, are their local minimums because the gradient vector is pointing away from each one of these points. And we also see that this saddle point, 0, 0, the gradient vector in certain areas is going into the saddle point, but in other areas is moving away from the saddle point. So what you're seeing here is actually, it's kind of like a generalization of the first derivative test from Calculus 1. So it's a generalization of the first derivative test from Calculus 1. And that's our first main idea that we can kind of see right here, is that in order to classify these critical points, we can do so with the first derivative using the gradient vector. If you look for points where the gradient vector is moving away in every region around the point, that's a local minimum. But if you look for and you find a point where the gradient vector is pointing in towards the point for all points around the critical point, that's a local maximum. And a saddle point is when you have regions where the gradient vector is pointing into the point, but also you have other regions around the point where it's pointing away from the point. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.